Okay, what if the data was explained by an exponential? Okay, exponential curves comes. One example I can think of is electrical circuits. If you have a RC circuit, you have an exponential. So if I told you to find A and B here, you could use some of the techniques we had just discussed, where you wrote down it like a polynomial form, you differentiated that with respect to A and B, and got the parameters A and B, but that tends to be more complicated than the trick I'm going to show you. So the trick here is, instead of trying to fit this equation the way it is, what you do is you take the log, taking logs. So log, and when I say log, it's base E. Right? Log E is basically 1, right? Because log E to the base E is always 1. Or log 10 to the base 10 is 1. Or log whatever, log A to the base A is 1. So this is log Y equals log A plus Bx. Okay, now here's the trick. Let Z be equal to log Y and C be equal to log A. Okay. How do you get Z? Well, Y is the data, right? You'll get data points. Just take the log of Y and you have Z. So we'll change the variables from Y to Z, but we can compute Z because Y is data, and you take the log of the data, that is the Y column, you get Z. C equals log A. This is like a benign transition. It's like log A is a constant, so C is a constant, A is a constant, log A is a constant, C is a constant. It doesn't matter what you call it, right? We have to switch it back. Now, if I write the equation, it's C plus Px, and we have a linear equation or linear regression here. So you could take an exponential curve and treat it like a linear curve just by taking logs. Same trick. Can be applied to Y equals AX raised to B. You could just take the log of the whole thing, and you'll see that that'll work too. Okay. C. Here's another equation which you could linearize. If you are given Y equals C1 plus C2 plus X, where you're told to fit C1 and C2 based on the data. Now that seems hard because when you take the derivative, you might get something like C2 plus X squared, right? When you take the derivative of Y with respect to C2, you get C2 plus X squared. And that's just cause of nuisance, because then in your regression, there'll be more complicated formulas. But you could do a trick here. What you can do is, I'm going to switch or divide the whole thing by, I'm going to switch C2 plus X and Y, or in other words, what I'm going to do is I'm going to multiply both sides by C2 plus X divided by Y. And I end up getting C2 plus X equals C1 divided by Y. Okay, now what I'm going to do is I'm going to say let C1 divided by Y be equal to, 1 divided by Y equal to Z. So now we have C2 plus X equals C1 divided by C1 times Z. But this doesn't look like it's in standard form, right? We are more used to Y equals mx plus b. So what we can do is we can divide by C1. So if you do that, I'm going to switch the sides. I'm going to take the right to the left. We'll have C2 divided by C1 plus 1 divided by C1 times X, which is similar to A plus Px, where A is C2 divided by C1, B is 1 divided by C1. So you basically have to do a linear regression on Z and X the way it is. and then work some steps backwards to figure out how A and B are related to C1 and C2. Okay, and D, a similar trick can be applied to y equals C1 plus C2 divided by x. I think I have a homework problem on D. Okay, so let's see how to use these tricks to solve a problem. Yes, I posted this on Blackboard. So the data is shown here, x and y. It is known that y equals a times exponential bx explains this data. You need to obtain a and b. So taking logs, the log on both sides, we have log y equals log a plus bx. Okay, let log y be equal to z and log a equal to c. So we have z equals c plus bx. So this is a problem in linear regression. So if you remember, if you want to compute C and B, I had written the formula for a form like this. So you can go back to linear regression, which is here. Oh my God, Sang. Okay, so if you go back to linear regression, we had computed A and B, and those were the formulas for A and B, right? Y equals A plus B. A is given by that formula, B is given by the formula down. And remember the form, it's A plus BX. So in our case, we have Z equals C plus BX. Okay, so Y is replaced by Z, and C is replaced by A. So I need to take these formulas, just substitute Y with Z, and I have the necessary equation. So I'll do that next. So here's the formula for C taken from that linear regression page we just showed. Summation xi zi, summation xi minus summation xi square, summation zi divided by summation xi square minus n times summation xi. Wait, I'm missing something. This should be square. Yeah. And then B is equal to summation xi, summation zi minus n summation xi zi. Okay, so what I'll do is I'll write down the answers to what C and B is, but then I'll show you the table which was used in order to get that. So I'll basically copy paste that from my notes in just a bit, but this basically was done using a table of the form we've used in the past. So C comes out to be minus 0.6407 equals 0.9794. Okay, so I'll just write here CB, C table, next page, and I'll put that table in a bit. It's a little tedious to copy that table because it will have like lots of numbers. So I don't want you to spend your time copying that, but you can refer to it later on. Okay, so assume that I've magically found those C and B. What do you do next? You have C and B. How do you compute your curve fit? Remember, you had A and B. We already found B, but we don't know what A is. So we need to go back to this formula. You can see that log A equals C. So if you want to find A, you just take the exponential to C. Yes, good question. So N is the number of data points. N equals, I think it's 10 or 11, 11 data points. Yeah, good point. I should have put that there. Okay, so let's compute A. Log A equals C. So A is exponential of C, but C is, by exponential, I mean e raised to C. E is, it's 2 point something. The calculator will give a more accurate value. C is something we found, 6407. So it turns out that A is 0.5270. In other words, y equals A e raised to bx. So A is 0.5270. E raised to b is from this page 0.9794. So 0.9794x. We put two things here. One is the data which let me put two things here. One is draw insert. Which you can basically sum the x, sum the z, sum the x square, sum the xz, and that all goes into here. Right? It's much easier. It's less error prone if you do that table. Otherwise, there's a chance that you'll make an error. And if you make an error, you can just figure it out from that table. The second thing I want to show you is insert is the curve itself. This is the data. Okay, y as a function of x. Remember, it's an exponential, right? So the blue is again the data, and the red is the fitted polynomial. So you can see that it explains the data pretty well, at least here, and then it sort of didn't do that a good job. But that's what the curve data fit gave you. Any questions?